Okay, hello everyone. My name is Joe DePaul, and I work on Project Helidon. So the agenda for today, I'm going to give you an introduction to Helidon. It's a Java framework for writing microservices. I'll talk a little about virtual threads, and then our Níma web server, which is new in the latest release of Helidon. That's based on virtual threads. I'll talk a bit about blocking versus asynchronous or reactive programming and some characteristics there, and then a few next steps and tips. And I'd like to thank Thomas Langer. He's our architect on Helidon, and a lot of this material came from Thomas. So first we'll talk about Helidon, just to give you an introduction. It's a framework for developing Java microservices. We put micro in parentheses here because your service could be quite small or maybe it's quite large. It doesn't have to be micro. But it's a framework for developing Java services. Your application with Helidon is just a Java SE application. So that means it runs in its own JVM. It has a main. Classes are loaded with the system class loader. Later slides, I might mention Jakarta EE. But that in no way implies an application server. So with Helidon, your application is just a normal Java application running in its own JVM. We are 100% open source. You can find us on GitHub, available under the Apache license. Of course, we have our open source support channels through GitHub issues and Slack. And then Oracle does offer commercial support for Helidon. Currently bundled with offerings including WebLogic, Coherence, and Verrazano, and we're continuing to look at other support offerings for Helidon. One thing that makes us a little different than some of the other Java frameworks is we support two programming models, or two API styles that you can pick from. So our foundational set of APIs we call Helidon SE. It's a kind of a small micro framework. It uses a functional Fluent style, so you use Fluent builders to construct your Java objects. It's a reactive or asynchronous based API. And we like to say no magic, right? There's no magic going on here. It's all very straightforward. Well, I don't know about straightforward. It's all very explicit and transparent. Helidon MP is our MicroProfile support. So MicroProfile was a working group that started a few years ago. It defines a set of kind of de facto standard APIs for writing microservices. It will be familiar for those that know Java EE or Jakarta EE programming, because some of the APIs came from Jakarta EE, like CDI and JAX-RS. And then MicroProfile defines additional APIs that I'll mention in a moment. It follows kind of a declarative, a version of control style programming, injection, annotation based, so a bit of a higher level programming model. A little block diagram here. So as I said, Helidon SE is our foundational API. Our MicroProfile implementation sits on top of that. And then while in Helidon SE, we do have a web server abstraction for you to define your routes and your routing and handlers, it is based on Netty. At least it is in Helidon 1.x to 3.x. It's based on Netty. That changes with Helidon 4. And again, some of our values, we like to be simple, transparent, no class loading tricks. There's nothing weird going on here, right? It's all very straightforward. Java, and we believe strongly in high alignment with the JDK and work closely with the JDK team on that. I mentioned MicroProfile as it is a set of specifications combining some key Jakarta EE APIs plus new MicroProfile APIs. It's supported by multiple vendors, and it promotes source code compatibility, right? So if you write a MicroProfile-based service, it will port pretty straightforward to other implementations of MicroProfile. It's not binary compatible, but source level compatibility is quite good. So here I kind of list some of the areas in MicroProfile, the specs or APIs that we support in Helidon. So at the bottom are some of the Jakarta EE APIs I mentioned. At the top are some of the fundamental MicroProfile APIs. You'll see they cover areas like observability for metrics and tracing and health, authentication, configuration, fault tolerance. And then in the middle are some of the optional MicroProfile APIs, LRA, reactive messaging, reactive stream operators. Again, these are all standards to one extent or another that we support in Helidon. And then we have a few Helidon-specific additions beyond what is defined in MicroProfile. As I said, with Helidon SE, it's our foundational API. So you kind of pick if you want to develop to MicroProfile or develop to our lower level SE API. As I said, it's a reactive programming model, heavily used reactive streams. We're based on the Java Flow API, if you're familiar with that. Heavy use of completion stage for asynchronous programming. It's a non-blocking API. The point here is to use it for highly concurrent services where you want to eke out a lot of performance. But generally, it has the same feature parity as I mentioned on the previous slide. Just the APIs you use will be different than you use with MicroProfile programming. In terms of like what is your application, how is your application packaged, we support 3 ways to package your application, all kind of very standard, nothing clever going on here. It's all straightforward stuff. So we support the Java executable jar. Your application code is in a jar file. The jar file has a manifest that identifies your main class and your class path. Your runtime dependencies are in a libs directory. Keeping them out of the jar makes it friendly for Docker images. Of course, you'll need a Java runtime to run that. So you can run java-jar in your application jar. So from a Docker perspective then, obviously, you would have a container with the operating system. And this is just standard vanilla Java, right? Nothing unique going on here. We also support JLink runtime images. So you can create a custom Java runtime. And we have some tooling to help you with this. So JLink lets you build a custom Java runtime for your application based on only the modules it needs. It does not like dependencies that are not well-formed Java modules, but our tooling helps with that. So you can take your Helidon application and with a specific build profile, you can generate a JLink image, and we generate the custom JRE for you. We also, in that case, generate a startup script to help with module path and things like that. And in that case, you start your application by running the start script. But again, that is straightforward kind of JLink custom Java runtime. And then the third packaging is GraalVM native image. So you may be familiar with GraalVM. It has a feature called native image. We support that as well. And so in this case, you compile the Java application to a native binary. And that native binary, of course, does not require Java runtime because it's native code. It's a native application. And therefore, you just need the operating system, and you just start it like any other program, native program on the operating system. So we have kind of a vanilla Java executable jar, JLink runtime image, and a GraalVM native image. And then kind of the last introduction to Helidon slide is this. We currently have 3 branches under active development. 2.x and 3.x are kind of in production, active development branches. 4.x is our kind of advanced development, currently in alpha. One difference between 2.x and 3.x is 2.x, we require Java 11, and 3.x, we require Java 17. So we are pretty aggressive about staying current and aligned with Java features. Another difference between 2.x and 3.x is Jakarta EE8 to Jakarta EE9. And so if you're familiar with that space in EE8, the API still use the JavaX Java package. In Jakarta 9, some of the specs changed to the Jakarta Java package. So that is technically an incompatibility that they introduced in Jakarta, and another difference between 2.x and 3.x. And then with 4.0, we currently require Java 19. In a couple days, it will be Java 20. And by the end of the year, Java 21, because we are heavily committed to virtual threads in Helidon 4. And those are in preview now in Java 19 and Java 20. And there is now a draft JEP for making them, promoting them to supported availability in 21. So that's what we're counting on. Okay, we're going to shift gears a little and talk some about virtual threads. So I'm just curious, how many of you are familiar with virtual threads or have used them? Oh, great. Okay, so some of you. All right, so JEP 425 is for Java 19, JEP 436 for Java 20. Those are the kind of the JEPs, the proposals for virtual threads in Java. Virtual threads are JVM-managed lightweight threads that help in writing high-throughput concurrent applications. If you've heard of Project Loom, they are a part of Project Loom. And as I said, they became a preview feature in Java 19. So starting with Java 19, a thread can be either virtual or what they now call platform. So a platform thread is your traditional Java thread you know, at least in recent history. It's the native OS platform thread. Virtual thread, as I said, is a thread implementation in the JVM that is very lightweight and that is scheduled onto platform threads. We'll talk about that in a minute. The virtual threads implement the thread API. So they are quite compatible with threads. So it's actually pretty easy to convert your code from threads to virtual threads. Now there are things to keep in mind, and we'll talk about some of that later, but they are generally compatible with platform threads. So some things that are unique with virtual threads, you can have a lot of them. You can have millions of them. We have benchmarks that run that are handling millions of transactions per second, and over the course of the benchmark, create and destroy millions and millions of virtual threads. And the JDK does a great job with that when we get excellent performance. As I mentioned, a virtual thread is scheduled onto a platform thread. That comes from the fork join pool, if you're curious. These virtual threads are scheduled and unscheduled on and off of platform threads as needed. We'll talk a little about that. They always have a group, the thread group virtual threads, and they have no permissions with the security manager. Not surprising since the security manager is deprecated. So I mentioned scheduling of virtual threads. A virtual thread mounts to a platform thread or a carrier thread to run. And so it is pinned to that thread and runs. When the virtual thread performs a blocking operation, such as maybe reading from a socket or maybe doing a completable future.get, then that virtual thread is unmounted from the platform thread. And that frees up the platform thread so another virtual thread can be scheduled onto it. Therefore, when you perform a blocking operation, you do not block a platform thread. Instead, you block the virtual thread, which is unscheduled. And what that means is blocking is not only okay in a virtual thread, it's kind of encouraged. It's great. You can block in a virtual thread, no problem. So what I have here is a little code snippet. And let's imagine this is running in a virtual thread. So you're running in the virtual thread. It's scheduled onto a platform thread. So the platform thread is running this code. You do the random next int. That's a non-blocking operation that executes. Then let's say you make an HTTP request with an HTTP client. And most HTTP clients these days support asynchronous programming. So in that case, that would be non-blocking because you get back a completable future. So that's a non-blocking operation. So now that HTTP regress is off, it's executing at some point in the future. All non-blocking so far, so we're still running on that carrier thread. But then, since I'm in a virtual thread, I know I can block. It's okay. So instead of doing some asynchronous stuff to execute in the future, or to be called when I'm executing in the future, I can just do response future.get. I can just block on that future and wait for the response. Because all I'm blocking is my virtual thread. And then at that point, the virtual thread is unmounted from the platform thread. That frees up the platform thread to be used, say, to run another virtual thread. And then once that blocking operation completes, then the virtual thread is mounted, scheduled back onto a carrier thread and continues running. Okay? So I was pinned to and running on a platform thread. As soon as my virtual thread performs a blocking operation, I am unmounted from the platform thread, freeing up that platform thread. Once the blocking operation completes, the virtual thread is remounted onto a platform thread and can continue execution. Okay? So I said virtual threads implement the Threads API. There are also some new APIs. So there's some factory methods, thread of virtual, thread of platform, so you can explicitly create virtual or platform threads. There's a new executor, the new virtual thread per task executor. Long name, but it says what it's good for. And one of the keys here is thread per task. And that's the way you should start thinking with virtual threads. That you can just allocate them for tasks. You don't have to worry about having too many or pooling them. You just allocate them when you need them. And therefore, they tend to line up well with your application's model of concurrency, right? If you have a web server like we do, or your web application, you're going to have many, many concurrent requests coming in. In the past, you had to try to adapt that concurrency to whatever the physical threads are, right? You only have a pool of them. You only have so many. So you have to do asynchronous programming so you don't block them. And you have to try to mesh that mismatch of concurrency. With virtual threads, you don't have to do that anymore. You can create a virtual thread for each connection, for each request. And then you just throw it away when you're done with it. And the JDK handles all the scheduling and unscheduling onto the platform threads. Okay, so to kind of summarize that, so with virtual threads, threads are no longer a scarce resource to be carefully pooled and managed, right? Instead, they are an abundant resource that can be created as needed to handle nearly unlimited concurrent tasks. So this is kind of a change in mindset you might have over standard traditional threading models. Okay, so we talked a bit about virtual threads. I'm going to come back to Helidon and talk about Helidon Níma, which is kind of our code name for our virtual threaded platform in Helidon. So previously I mentioned our two programming models. We had Helidon SE for high concurrency, high performance, but a little difficult to program in, right? It's asynchronous programming. Reactive programming is hard. It's hard to troubleshoot. It's hard to maintain. We're going to talk about that a little more. There is a learning curve there. We have found with our customers, not many write good, robust, correct asynchronous code because it's really hard. Or you can choose Helidon MP, which is a much more friendly and approachable programming style. But there you can run into some bottlenecks because it tends to be a blocking programming model. And so you're limited by the number of traditional threads, platform threads. And yes, there's some asynchronous programming constructs in Jakarta and MicroProfile, but it's not the design center. So you kind of have a bit of this trade-off. But with Helidon Níma and Helidon 4 and virtual threads, you don't have that trade-off anymore. So you now get the scalability of reactive programming with the simplicity of a blocking programming model. And we wrote this code from the ground up for virtual threads. This is not a retrofit to an existing server. A lot of existing web servers are going to experiment with virtual threads and retrofit part of their engine to virtual threads. But as far as I know, we're the first, at least the first full-featured web server that is written from the ground up to take advantage of virtual threads. And we did that in conjunction with the JDK team. We're getting performance comparable to Netty. Yes?
Is the plan to just completely replace Netty with Níma going forward?
Yes. Yes. So we are, yes. So today, we're built on Netty. Our plan for Helidon 4 is Netty's going to be gone. In terms of performance, we get performance comparable to Netty, to raw Netty. Netty, if you write a raw Netty application, it will be faster on some benchmarks. We're actually faster in others. So I'm not going to say, yeah, we're faster than Netty, but we're comparable. And that's not really the big news, right? The big news is the ease of programming with this high concurrency. And it's available in Maven Central today. So we have shipped 4.0 Alpha 5. You can play with it today. We're going to be starting milestone releases soon. We're targeting to release 4 GA in conjunction with Java 21 in the fall. That's our plan. But you can play with it today. And in the hands-on lab, you can literally play with it today. Oh, OK, so the Níma web server, this replaces Netty, but also provides a higher level abstraction than Netty does. So if you've ever programmed directly to Netty, it's kind of a lower level API. But it essentially replaces Netty as our web server. Right now, it supports HTTP 1.1, 2, gRPC, and WebSocket. It has an extensible design for other TCP protocols. We're also looking at adding UDP as well. And we're making testing support kind of a first-class citizen, so it's easy to write unit and integration tests with it. So to look a little about the threading model used in the Níma web server. So I don't know if any of you have written for a server from scratch that handles network and socket connections, but you usually have a server socket listener, right, which waits for connections. And in Níma, this is a platform thread, okay? But typically there is one per port. So often that means just one of these for your application, maybe 2, 1 per port. But as soon as a connection comes in, then a virtual thread is created to handle the connection. And with HTTP 1.1, we have 1 virtual thread per connection. So remember with HTTP 1.1 on that connection, you can have keep alive and multiple requests coming in, but the requests will be sequential on that connection. So you're just handling 1 request at a time on that connection. And you have, with Helidon Níma, a virtual thread dedicated to that connection. That means that's all yours, right? For processing that request, that thread is all yours. You can do whatever you want. You can block. There's no sharing, right? With like Netty, you have a small pool of handler threads, and you never want to block those. But with Níma and virtual threads, of course you can block it. With HTTP 2, there's a virtual thread to handle the connection. And then if you know HTTP 2, with that protocol, there is 1 or more streams multiplexed across that connection, where each stream represents a sequence of requests. So in that case, we then allocate a virtual thread per stream. So you have 1 for the HTTP2 connection to manage the connection, and then 1 is allocated per HTTP2 stream, again, giving you this dedicated virtual thread for your request and response. And as I say here, all routes or handlers, all the business logic or your code that's executed with the request, by the request, is executed within a virtual thread and can block as needed. And that's kind of the big news here. Okay, so I hope you can see this all right. So here I kind of have a comparison of reactive programming, asynchronous versus blocking. So here I have two handlers. This is kind of using our web server API. So this is not MicroProfile. This is our lower level web server API. On the left is what the handler would look like with Helidon 3 using a reactive or asynchronous programming model. On the right is how it looks in Helidon 4 with the Níma web server. These two handlers do the exact same thing. They get a request. The request contains a parameter for a count. And then the handler fans out and makes count, say 5, requests in parallel to HTTP requests, say to a remote service. So it's like a fan out. It then waits for those 5 requests to complete, and then it aggregates the responses from those 5 requests into one response that the handler then returns. So it's a fan out. A request comes in, fan out, 5 client requests to 5 services, say, wait for them to come back, and then aggregate the response and return it. So to do that in a reactive way is on the left. In that case, you can't block the netty thread waiting, or the physical thread handling this, you can't block that and wait for 5 clients to respond to you. So you need to do it in an asynchronous fashion. And here's some code. I don't claim to fully understand that code. It took Tomas and another guy 20, 30 minutes to write that code. And here you're using some reactive stream operators. You see multi with a range for the count. Good old flat map shows up to help you map that into the client requests, which are buried down in there. There's a client.get.request, so that's some asynchronous client doing the client request. And then you need to flat map that again with function.identity. Don't ask me what that is. I don't claim to know. And then you collect that in a list and then do another map so that you combine the results. And by the way, if there's an error, do this. And then finally at the end for single, you, I guess, collapse everything to a single and then do the send at some point in the future. So this code is hard to understand. It's awful to step through on a debugger. I don't know if you guys have ever stepped through these fluent streams on a debugger. It's icky. If you run like a profile or a performance analyzer on this code to identify hotspots, and you want to see context in the call chain, it can be terrible. You want to set breakpoints and debug, it's tough, right? So there are people, probably all of you, that are really good at this and can do this really, really well. For a lot of us mere mortals, we can't. It's hard. And we've seen this with our customers. It's hard. Okay, now let's look at the code on the right, which maybe represents stuff you wrote back in college, maybe. And so what do we do there? Well, first of all, we're going to need a thread pool and executor because we're going to want to do these 5 client requests in a thread pool. That's fine. So we get the count out of the request. We allocate a list, a data structure, yay, to hold my futures that I fire off in this next loop. A loop! Yes, doesn't that feel good? A loop. So we have a loop that submits the remote client call to a thread pool, a virtual thread pool, so we don't really care how many we do here. And we just save the futures. It's doing things asynchronously fine. It's giving us back futures, that's fine. But we store those in a data structure, that's great. When we're done submitting those 5, bam, 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 that's all non-blocking, right? We then come to a second loop where we're going to aggregate the response, construct the response. So then we just, again, a lovely loop. We loop through the futures, and we can and then we just do the blocking operation get, okay? And we don't care if that blocks for a second or 5 seconds or maybe a minute. We don't care because we're in our virtual thread. As soon as we do that blocking operation get, the virtual thread is unmounted from the physical thread. That physical thread is free to be reused. The virtual thread hangs out until the blocking operation is complete, at which point it's rescheduled. So this is not only okay, it's encouraged. And you all know you can step through that code on the right with the debugger. You all can do that, right? If you get a stack trace, it'll tell you exactly what you want it to tell you. If you profile, it'll tell you what you want to do it. So it's going back the way to do programming that you and I were meant to program. Okay? All right, off soapbox a little bit, but that's to give you a contrast. And that really is the message here. Virtual threads, they're great for concurrency and performance. That's not the lead, though. The lead is being able to program on the right and still have awesome performance. By the way, if you want to see this code, play with this code, you can try it in the hands-on lab later today if you want to come by. Right, Magic?
Correct.
Correct. OK, so I went on a bit about kind of those two handlers and that level of our API. I did want to mention, well, Joe, what about MicroProfile? You know, how does this work with that? How does that work? And yes, it does. In fact, your Helidon 3 MicroProfile app will run on Helidon 4 with almost no change. In fact, pretty much no change. And then you will be running on the Níma web server. You'll be getting all the benefits of virtual threads. And in that case, you will not have had to do any change. If you happen to have written a 3.x Helidon SE application that used our lower level asynchronous APIs and you want to go to the new blocking model, then that obviously is a more involved porting effort. But if you've already written a MicroProfile based app, it just moves over and it works. You can also try this in the hands-on lab. We do a little thing where you create a Helidon 3 app, MicroProfile, and then make 2 changes and it runs on Helidon 4. I'm not going to go over a bunch of performance numbers, but this is kind of just showing the dark boxes was our reactive programming model using platform threads, and the right, faster requests per second is using virtual threads. And we kind of have the same code being able to switch between the two. So we do good. Performance is good. We're really happy with it. It's almost astounding the performance we get on HTTP2 with multiple streams. Not that many applications do that these days, but the performance is profound with that. All right, so I'm doing OK. So I'm going to switch a little to tips and maybe some caveats. Like I said, you just can't blindly adopt virtual threads. You have to be aware of a couple things. So first of all, there are times when a virtual thread cannot unmount from the carrier thread. So there can be some OS level limitations. And I know the JDK team is working on these. And some file system operations are an example of that. So that's one thing to watch out for. The Java guys will have more details on that. But that is one area where the virtual thread will stay mounted to the carrier thread, even though a blocking file system operation is being performed. Another one is object.wait. And I don't claim I understand why, but that's a JDK limitation. When these operations occur, the JDK compensates by adding a platform thread to the fork join pool. So the JDK is saying, oh boy, I know it's reasonable for you to do that, but we can't unmount the virtual thread, so we're going to temporarily add another platform thread. So the JDK tries to compensate a bit for that. There is another category of pinning where virtual threads stay pinned to a carrier. And these cases are a little more serious because the JDK doesn't compensate by adding an additional platform thread. The big one is synchronized blocks. So if you've done any reading with virtual threads, you will have heard avoid synchronized blocks, avoid the synchronized keyword. That's generally true. Obviously, if you have those blocks at startup or when you don't have high concurrency, then it's okay, right, to use synchronized. But if you have that in code that you want highly concurrent, then you want to eliminate the use of synchronized. Now, the good thing is there's usually ways to refactor your code to eliminate the synchronized keyword. You can use locking constructs from Java util concurrent, and those all work great with virtual threads, okay? So the message here is if you have synchronized blocks and concurrent code, you want to refactor those and use other locking from Java util concurrent. Native methods and foreign functions are other things that can pin a thread to a carrier. Those tend to be less common. So you want to avoid that. Okay, a few lessons learned. At least on our team, we had some developers who've been really in asynchronous programming, doing it for a number of years, and they're having to unlearn some habits as they remember that they can just do normal blocking programming. Everything is easier. It's easier to learn, easier to write, easier to read, easier to debug, easier to maintain, easier to profile. Everything is easier. Now, of course, this stuff's new. And so there are libraries out there that have not been optimized for virtual threads. They generally work fine, but there can be cases where the threading model matters. And so you just kind of have to keep this in mind. If you run into a performance issue, for example, it could be because a dependent library is assuming a different threading model. I talked about refactoring synchronized to Java util concurrent locking. One of those areas that you have to take a close look at is the use of thread locals. So while virtual threads do support thread locals, often the use of thread locals assumes a threading model. What I mean by that is often the use of thread locals, the code that is setting the thread local is assuming there's going to be relatively few number of threads. That might not be true with virtual threads. The code using the thread local might be assuming that thread's going to be reused. So I'm going to do an expensive operation that computes something kind of clunky, and I'm going to put it on a virtual thread so the next thing that runs on the virtual thread can just pick it up off the thread local. Not the virtual thread, the physical thread can just pick it off the thread local, use it for caching. Of course, if the code is doing that, that does not work well with virtual threads, because usually with a virtual thread, you create the thread, you run it, you throw it away. And now that code that was benefiting from caching in the thread local is now paying the penalty of that and not getting any of the benefit. So the message here is if you use thread locals and you're switching to virtual threads, you need to take a close look at how you're using the thread locals. Some use cases may be fine, others might not. The JDK is working on a new feature called scoped values. It's kind of a more robust API for caching and sharing information between threads. So keep an eye on that. I think that is preview in Java 20, so you'd be able to experiment with that today. And Tomas said virtual threads are the best improvement in Java ever, okay, ever. So we think this is a big deal. And it's really going to change programming in Java, at least concurrent programming, forever. All right, some things to keep an eye on. So JEP 428 is something called structured concurrency. It was a preview in Java 19. This lets you take tasks in your Java program and create a relationship between them, organize them hierarchically. It works well with virtual threads, especially if you're spinning off a lot of virtual threads to do different tasks. This helps you to manage that. So that's available as a preview in 19 and 20. So take a look at that. I mentioned scoped values, which becomes a preview in 20, which has just been released, I think. So take a look at that. Virtual threads is a preview in 19 and 20 and is set to become final, promoted to final in 21. So the JEP has not been assigned a number, at least as of yesterday. But you can keep an eye on that for the status of virtual threads in Java 21. And there's a link there to issue or the draft JEP for that. There's not much change in virtual threads between 19 and 20, and not much change at all between 20 and 21. I think the main change between 20 and 21, I think they're proposing to support thread locals, have that enabled by default. Right now, I think you have to enable that explicitly. So those are a few things to keep an eye on. Next steps. So as I mentioned, there is a hands-on lab today. If you haven't signed up, no problem. Come anyway. You'll be able to do some hands-on programming with Helidon and virtual threads. It's a pretty simple lab, and then you may have some time to explore on your own, but you'll be able to get started. And if you're interested in Helidon, you can come visit us at helidon.io. And that's the end of my presentation for today.